So, let us complete the unfinished task. We started with a sphere which rotates about z axis with constant angular velocity omega. The surface of this sphere has a uniform surface charge density which is sigma, and we wanted to know the magnetic field inside because of this current which is on the surface. And then we did some electrostatic analogy and finally obtained that if we write the corresponding this k x, k y, k z, they are given by these expressions, and then we could find a case, electrostatic case, where you have a uniformly polarized dielectric sphere, and that we took the polarization we took in minus j cap direction with this constant c here, and then we found that the charge density which appears is given by this expression, and from there we could derive that finally it is minus c sin theta and sin phi. Now, this charge density is its same expression, it's same as it is here minus c sin theta sin phi, and therefore, if this is the charge density, then electric field is given by this expression. Using this, we got the electric field which was a constant in y direction, and therefore, the potential was this. Then putting this y as r sin theta and sin phi, we wrote this. This is essentially in Cartesian coordinates, if I write, it is this minus c over 3 epsilon naught, and that epsilon naught will go there. This will be minus mu naught c by 3, minus mu naught c by 3, and then y. So, this is, do not take this into this. So, in Cartesian coordinates, if you write, it is this. In spherical coordinates, you write this, but this is a x, remember, this is x component. So, we are using Cartesian components. So, the next task is to find this a y. How do I find a y? So, the current density, surface current density in y direction is given by c sin theta cos phi. So, if we can find a charge distribution with this kind of surface charge density, and then if we can get the electric potential, similarly we will be writing this. And doing that is also not very difficult. The only thing we have to do is to take this p, take this polarization in I cap direction. Okay, so, if we take this p in I cap direction, c I cap, if this is the polarization, we have a dielectric sphere with uniform polarization c I cap, then the charge which will appear on the surface, sigma charge density, surface charge density, that is given by p dot r cap, and once again this p is c and then I cap here, and dot with r cap vector, and r cap vector will be r sin theta cos phi, r sin theta cos phi, and r is also not needed because we only need the unit vector. So, sin theta cos phi, this much in I cap direction, plus sin theta and sin phi, that much in j cap direction, and plus cos theta in k cap direction. So, that is the unit vector in r cap direction. Remember, we did this previous case also, and then I dot I will give you result, I dot j is 0, I dot k is 0. So, this is equal to c times sin theta and cos phi, which is exactly the same here. ky, c sin theta cos phi. So, if I treat this as a surface charge density, what is the electric potential? That expression will give me the y component of the magnetic vector potential. And to know the electric field and this potential is quite easy, because electric field is minus p over 3 epsilon naught, and p is here, p is here c I cap. So, this is minus c and then I cap over 3 epsilon naught. The electric field is in x direction, and therefore, the potential will have only x dependence, not y dependence, not z dependence, and the potential is, you can write it very easily, c over 3 epsilon naught times x. Ensure that Ex, which is minus del v del x, if you differentiate with respect to it x and put a minus sign, you will get minus 3 by minus c by 3 epsilon naught, and that is it. You only have Ex, you do not have anything else. So, this potential corresponds to this field. So, we know the potential now, and therefore, we can immediately write this Ay. This is same as this, is same as this. For this charge, surface charge density, we are getting this as the electric potential, and therefore, with this current density, the same expression will give me the y component of magnetic vector potential. So, Ay is equal to 1 by epsilon naught, I will be writing mu naught. So, it is mu naught c by 3, and then x, and x is r sin theta and cos phi, and Az is 0. And in terms of Cartesian coordinates, it will be mu naught c by 3, and then x. So, you can write it this much I cap plus this much j cap, but hybrid, you are using r theta phi and also I cap j cap, and we have to finally write the magnetic field, which is curl of A. So, it is easier to use these expressions. So, that A vector you can write as, this is I component Ax. So, it is minus, or let us take mu naught c by 3, that we can take common, mu naught c by 3. So, minus y I cap, and here plus x j cap, right. Ax is this much, Ay is this much. So, the vector A is this I cap plus this j cap. So, mu naught c by 3 is here, minus y I cap and plus x j cap. So, we have gotten the magnetic vector potential inside this sphere, rotating sphere. So, now I can erase all this. So, magnetic field B, and this is all for inside the sphere, which is curl of A, and in Cartesian coordinates it is easy to remember. Write I cap here, j cap here, k cap here, del del x here, del del y here, and del del z here, and then Ax is this mu naught c by 3, again you can write common, mu naught c by 3, then x component is here minus y, so you write minus y here, and y component is plus x, so you write plus x here and 0, x component, y component, and z component, and this is mu naught c by 3. Then I cap del del y of 0 minus del del z of x, this is also 0. So, no I cap, j cap if you take j cap, del x of 0, del z of y, so that is also not there, k. So, it is k in k direction, and how much it is? How much it is? Very simple, del x of x and minus del y of minus y. So, 1 and minus 1, that is 2. So, it is 2. That is it. B, we got B is 2 by 3 mu naught, and what is C? C was sigma r omega. For this constant we had written C. Sigma is the surface charge, real surface charge density, not virtual, real surface charge density on the given sphere, and r is the radius, capital R, omega is the angular velocity with which it was rotating. So, this is C. So, 2 by 3 mu naught C, and that is k cap. So, inside this rotating sphere, the magnetic field is constant. It is constant in magnitude and in direction. Magnetic field is this way, everywhere, magnetic field is constant inside this. You can extend it for outside the sphere, this same electrostatic dielectric sphere, that current density you can, surface charge density you can obtain from there, and then for outside it will be a dipole field, and the dipole potentials are also known. So, from there you can write what is the magnetic field outside. Okay. Now, the last part in this chapter is, if the magnetic field is known, can I write vector potential? Here the entire exercise was get the magnetic vector potential and from that get the magnetic field. But maybe we will be interested in situations where the magnetic field is known, but we want to write this vector potential. Now, that is also very simple in fact, because again if you look at the equations for vector potentials, these are the two equations. And why divergence and curl are given so importance? Because once you know the divergence everywhere of a field, once you know the curl everywhere in the space, and if you know the value of that field, that vector field at the boundary, and if your boundary is at infinity, normally it is 0, the magnetic field, everything is taken 0 there. So, we know that anyway. So, once we know these two, this is uniquely specified in the entire space, entire region for which you are doing. So, that is why these two, if you can handle these two, sufficient. And for magnetic field, the equations are divergence of B is 0 and curl of B is mu naught J. So, you can see that the two mathematical structures are identical, and if current density is given and you know because of that current density how much is the electric field, if you know for the given current distributions, then using this analogy you can also say that okay, the way this B is obtained from J, in the same fashion this A will be obtained from B, right. If you know that okay, this is the current distribution and this is the corresponding magnetic field, and if that same expression, algebraic expression for that current density, if you put here, then identical equation, identical algebra, identical solution, that will give you A directly. So, what I am proposing is, if B is known to you, if B is given means as a function of space points everywhere, the expression for B is known. So, if B is given, treat treat this B as, or B by mu naught as J. Mentally, it is virtual, it is not real. B by mu naught will not have the same dimensions as J. So, just look at the mathematical expression. You know B is given. So, just look at the mathematical expression. It is a function of x, y, z, and just assume that this function is giving you the current density, and if that is the current density, what is the magnetic field? That expression you write, and that expression will be just the expression for A. Okay. So, let me explain it with an example. Let us take the example of a long solenoid. We have a long solenoid, and current I goes through every turn, and this is, let us say, z axis, the central axis is z axis, and the number of turns per unit length n is n. So, if this distance is delta L, then there are the number of turns is, let us say, delta n, these many turns, 1, 2, 3, 4, 5. So, number of turns delta n in this delta L length, this delta n divided by delta L, this is your small n. So, small n is number of turns per unit length of the solenoid. And we want the magnetic vector potential. We want magnetic vector potential everywhere, inside, outside. The solenoid and the current and the number of turns per unit length, it is given. So, how do I go about it? So, the magnetic field, you know the magnetic field. Inside a solenoid, you know the magnetic field. So, the magnetic field here will be mu naught n I in k cap direction. This is given. Given means we know it. Given, this is given, that this much is current and these many number of turns, etc., and we know that, okay, this is the magnetic field, and corresponding to this magnetic field we want the magnetic vector potential. So, we assume, we take mentally, we take this expression or B by mu naught, this is n I k cap, and we pretend that this expression is current density J. Whatever B by mu naught is there, that expression, we pretend that this is expression for the current density J. So, if now this is our virtual calculations, if J is equal to n I k cap, if J is equal to n I k cap, what is B? We will calculate this. If this J is n I k cap, then what will be the B? That same expression will be the expression for this vector potential A. Now, this is the volume, inside this volume, if this is J and outside it is 0, remember, outside it is 0, this is inside. If I write the complete thing, this is inside and it is 0 outside, and hence here also J is this much for inside. Let us say this radius is r, and then this distance is, let us say, some s. Okay. So, inside and 0 outside. So, if this much of current density, which is constant, which is uniform, n into I, n is given, I is given. So, it is a constant current density inside this volume, and outside there is no current density. So, look at that another problem which is coming from this assumption. We have a volume, we have a cylindrical volume, and then the radius, this whole radius is r, this whole radius is r, and then for s less than r, that means inside you have a current density in k cap direction. So, that means you have a current this way, you have a current this way, and how much is the current? It is a uniform J, J is Ni, J is Ni, J is Ni. That means the total current, if I ask what is the total current crossing this, the total current will be Ni into pi r square. Okay. And nothing outside, no current outside. Inside you have a constant current density Ni in k cap direction. Total current, if I ask, it will be just Ni pi r square. What is the magnetic field? If this be the case, what is the magnetic field? You have solved this problem. If you have a cylindrical volume and then a constant current is going uniformly distributed, you know how to do that. And it is very easy. If you do not remember, suppose you are somewhere here at a distance s from the axis. So, what we will do, we will just take a circular loop here with this radius, and the magnetic field is in phi cap direction. If the current in z cap direction, magnetic field is in phi cap direction, and therefore use Ampere's law. Use Ampere's law, that is how we derived it earlier. This is B dot dl is equal to mu naught I enclosed, and then this will be B into the periphery 2 pi s. I am skipping all those arguments of symmetry that this is in phi cap direction and not in s cap direction, not in k cap direction, etc. We have done it in this course itself, and this side it will be mu naught Ni times pi s square. This is pi s square, this area is pi s square, and the current per unit area is Ni, the current density, and therefore this current density Ni times pi s square, that is the current enclosed. And so, B is equal to mu naught Ni pi s square divided by 2 pi s. So, it is mu naught Ni by 2 into s in phi cap direction. So, we have gotten the expression for B, and this expression gives me this expression of magnetic field, gives me the vector potential inside. It gives me the vector potential because we have solved this, we have solved this, is the same equation, and therefore, A inside S less than capital R is mu naught N I by 2 S phi cap. What about outside? Outside is even simpler, that anyway I also remember the formula, and therefore you also remember the formula. If it is outside point here S at a distance S from the axis, and you have this much of current I, going in z direction, what will be the magnetic field here. So, you can just do this same exercise. This will be a circle on which you will be applying Ampere's law. This side you will get B into 2 pi s, but that side enclosed is only this much. Current is only here, there is no current here, there is no current here. And therefore, you will write as for outside S greater than R, you will write this B into 2 pi s is equal to mu naught n I pi capital R square. This is capital R, this is capital R. So, current is only through this area, which is pi into capital R square, and therefore, B is equal to divide by 2 pi s mu naught n I pi R square by 2 pi s. So, this is B is mu naught n I by 2 R square by s, R square by s in phi cap direction. And therefore, A for s greater than R is equal to mu naught n I by 2 R square by s phi cap over. Gotten final result. Okay. So, once again I repeat the recipe. What we have, the problem is, if I know the magnetic field in a particular region, can I write the vector potential, corresponding vector potential? And if I do that, it is easy. You assume that that given magnetic field divided by mu naught, this is an expression for a current density in that region. If that is the current density, what would be the corresponding magnetic field? Write expression for that, and that expression will actually give you the expression for A. So, that is how we handle magnetic vector potentials. And an interesting relation, just a short relation, is also good, since curl of A is equal to B. You can write A dot dl is equal to, this is on a closed loop, curl of A and then dot dA. Remember this, this is our Stokes theorem, valid for any vector field, no physics involved, just mathematics. Definition of all these quantities, curl and line integral, closed loops. A dot dl is equal to curl of A dot dA, Stokes theorem, valid for any vector field A, and curl of A is B. So, this is B dot dA, and this is on a loop, this is on a closed loop with an arrow, and this dA vector, area vector, is here, right hand side you have to integrate on this. So, B dot dA is the flux of magnetic field through this area. So, that is also a relation which is sometimes useful. A dot dl is giving you flux, magnetic flux through that area, whatever is that integration loop here, through that area, this gives the magnetic flux. So, we will close our chapter here, and a new chapter will be started next.